Far out in the cosmos, hidden among billions of stars and galaxies, exists a structure so strange and so perfectly crafted by the universe that it seems almost unreal, Hoag's object. This galaxy is unlike any other, a breathtaking enigma that challenges nearly every conventional idea we have about how galaxies are born, how they grow, and how they evolve. While most galaxies follow patterns we've come to recognize, spirals swirling in elegant arms, ellipticals glowing like cosmic spheres, or irregular galaxies twisting in chaotic forms, Hoag's object stands apart, breaking the rules and defying expectations. Its sheer symmetry and uncanny perfection make it one of the greatest mysteries of the cosmos, a silent riddle suspended 600 million light-years away in the constellation Serpens. And yet, despite decades of study, its origin and nature remain unresolved, forcing us to confront the possibility that the universe still holds secrets beyond even our boldest theories. In 1950, an American astronomer named Art Hoag was carefully scanning the night sky in search of distant celestial objects when he stumbled upon something that made him pause. He was working at the Palomar Observatory in California, a place where some of the most advanced telescopes of the time were peering deep into the cosmos. Through the eyepiece, he noticed an unusual circular structure that looked unlike anything he had ever seen before. At first glance, he thought it might be a planetary nebula, the glowing remnants of a dying star, or perhaps some kind of optical illusion caused by the telescope itself. But the more he studied it, the more convinced he became that he had discovered something unique. This peculiar structure was later confirmed to be a galaxy, yet it bore almost no resemblance to the galaxies astronomers had grown accustomed to observing. Spiral galaxies, with their elegant arms twisting out from bright central bulges, dominated the universe alongside massive elliptical galaxies and the more chaotic irregular types. But this new discovery seemed to fit nowhere. It was a glowing yellow core surrounded by a ring of bright blue stars, with a dark, seemingly empty void separating the two. The sharpness of the separation and the near-perfect symmetry of the circle were so strange that even Hoag himself was baffled. For decades, galaxies had been classified into neat categories, but this object seemed to defy every one of them. What made the discovery even more astonishing was the timing. In the mid-20th century, our understanding of galaxies was still in its early stages. It had only been a few decades since Edwin Hubble had demonstrated that the Milky Way was not the entire universe, but merely one galaxy among billions. Astronomers were still piecing together the mechanics of star formation, the role of gravity in galactic structures, and the large-scale evolution of cosmic systems. To suddenly encounter a galaxy that looked like a cosmic bullseye with no apparent explanation was like finding a puzzle piece that didn't belong to the picture. It wasn't just rare, it was almost unthinkable. As images of Hoag's discovery circulated in the scientific community, astronomers struggled to explain what they were seeing. Some suggested it could have been the result of a galactic collision where one galaxy had plunged through the middle of another, creating a rippling shockwave that spread outward to form a ring. Others thought it might have been an artifact of gravitational resonance, where tidal forces somehow shaped the stars into a circular pattern. But these ideas were still speculative, and the evidence didn't fully align with either explanation. The galaxy had no visible scars of collision, nor did it display the chaotic disturbances that usually accompany gravitational distortions. Instead, it sat quietly in space, serene and symmetrical, as though it had been intentionally crafted. For Art Hoag, the discovery was both thrilling and frustrating. On one hand, he had uncovered a genuine oddity, something that would forever bear his name in the annals of astronomy. On the other, he and his contemporaries could not offer a satisfying answer for how it came to be. In science, the most valuable discoveries are often those that cannot be immediately explained, because they force us to question existing assumptions and push the boundaries of knowledge. Hoag's object quickly became one of those rare discoveries, a cosmic anomaly that challenged the very foundations of galactic theory. Even today, decades after Hoag first laid eyes on it, the sense of bewilderment persists. Modern telescopes have captured sharper, more detailed images of the object, and yet the mystery has only deepened. The perfect symmetry, the distinct separation between the core and the ring, and the sheer improbability of its structure continue to haunt astronomers. What Art Hoag found that night was more than just a galaxy. It was a riddle written in starlight, one that continues to confound even the most advanced models of astrophysics. His discovery became a reminder that the universe still contains surprises far beyond the limits of our imagination, and sometimes those surprises arrive in forms that look almost too precise to be natural. When we look closely at the strange formation that is Hoag's object, what immediately stands out is its bizarre structure, a design so unusual that it almost feels as though it doesn't belong to the same universe as everything else we know. At its heart lies a glowing yellow core, an ancient spheroidal concentration of older stars that give off a warm golden hue. This central region looks somewhat similar to the bulge of an elliptical galaxy, where ancient stars burn more dimly, their life cycles stretched into long cosmic ages. But surrounding this quiet, golden nucleus is something that makes the galaxy so hauntingly unique, an almost flawless ring of brilliant blue stars, hot and young, burning with ferocity and energy that sharply contrasts the mellow, ancient glow of the core. What makes this contrast even more striking is the separation between the two. Unlike spiral galaxies, where stars and dust transition smoothly from the core outward into spiraling arms, Hoag's object has a distinct empty gap, a dark moat encircling the core, where hardly any stars are found. This void is unusual, because in most galaxies the distribution of stars, gas, and dust is continuous. Here, however, it seems as if something carved out the middle, leaving behind a barren gulf that separates old from young, past from future, silence from activity. It is this strange emptiness that makes the galaxy look like a celestial bullseye or a cosmic ring floating in the darkness of intergalactic space. The ring itself, meanwhile, is a wonder of its own. The blue stars within it are massive, short-lived giants, the kind that form in regions of intense star birth. Their brightness signals that Hoag's object is not just a fossil of the past, but a galaxy still alive, still in the process of creating new stellar systems. And yet, the ring is astonishingly uniform. Instead of appearing clumpy, uneven, or stretched into distorted arcs, as one might expect from a galaxy shaped by chaotic processes, the stars form a near-perfect circle, smooth and balanced, as though the universe had drawn it with a compass. Such symmetry is rare in cosmic structures, which are usually shaped by turbulence, gravity, and collisions. From a structural perspective, Hoag's object feels alien when compared to our galactic neighbors. Spiral galaxies like the Milky Way display arms filled with gas and stars, radiating from a bright center, while elliptical galaxies are smooth, featureless balls of ancient starlight, and irregular galaxies are often messy and chaotic. But Hoag's object doesn't belong to any of these families. Instead, it stands alone, with its glowing yellow core, its mysterious gap of darkness, and its radiant blue halo of stars encircling it like a cosmic crown. Astronomers who first studied its detailed images described its appearance as eerie, almost artificial. The sharp contrast between the old yellow core and the youthful blue ring is not something normally seen in galaxy formation. Normally, galaxies blend their populations of stars, with older stars and younger stars scattered across overlapping regions. But here, the segregation is clear and deliberate, as though two entirely different galaxies had been fused together, yet without the scars and distortions usually seen in galactic mergers. It is almost as if the laws of galactic formation bent themselves around Hoag's object to create something uniquely symmetrical, something that feels more like cosmic art than random evolution. The bizarre nature of its structure is amplified by scale. This is not a small feature. The entire galaxy is about the size of the Milky Way, roughly 100,000 light-years across. That means the ring itself stretches tens of thousands of light-years wide, and the empty gap separating it from the core is vast enough to contain entire dwarf galaxies within its silent expanse. To stand inside the galaxy and look outward from its yellow core would mean gazing through a region of near emptiness, only to see a magnificent, glowing halo of brilliant blue stars circling the horizon like a cosmic halo. It's a vision so surreal, it's difficult to even imagine what it would be like from the inside. This bizarre arrangement, core, emptiness, and ring, makes Hoag's object one of the most visually striking galaxies ever found. It doesn't simply stand out because of its shape. It stands out because it represents a configuration that seems to break the expected rules of galactic evolution. Every time astronomers study its images, they are reminded that nature is capable of creating structures so symmetrical, so deliberate, that they feel less like the product of randomness and more like the design of some hidden cosmic mechanism we do not yet understand. It is this oddness, this departure from the expected, that makes Hoag's object a true cosmic oddball. What makes Hoag's object so mesmerizing, beyond its strange ring and luminous core, is the sheer perfection of its symmetry. Across the vast canvas of the universe, galaxies are born through chaos, clouds of gas collapsing, matter colliding, gravity tearing and stretching structures until they settle into the familiar spirals, ellipses, and irregular forms we know. Even the most orderly spiral galaxies, like our Milky Way or the majestic Andromeda, are not perfectly symmetrical. Their arms are uneven, their centers slightly off balance, and their outskirts frayed by encounters with smaller galaxies. Nature, after all, tends to create beauty through disorder, not precision. And yet, Hoag's object sits in space as a near-perfect circle, its core aligned exactly at the center of its glowing blue ring, with a flawless gap of darkness separating the two. This is not simply rare, it is almost unheard of. The improbability lies in scale. We're not talking about a small planetary nebula a few light years across, where localized forces can sometimes create striking circles or shells. Hoag's object spans nearly 100,000 light-years, placing it among the giants of the cosmos. To maintain such symmetry across such an enormous structure, despite the constant pull of gravity, the turbulence of star formation, and the disturbances of intergalactic space, borders on the impossible. One tiny irregularity in gravitational distribution, one small interaction with a passing dwarf galaxy, or one asymmetrical burst of star formation should be enough to distort the circle. And yet, when we observe Hoag's object, we see near perfection, as though every chaotic variable in the universe conspired to cancel itself out. Astronomers often describe galactic evolution as a messy process, filled with accidents. Collisions between galaxies are common. Stars form unevenly in clusters. Dust clouds scatter light in random patterns. Symmetry on small scales sometimes emerges. Rings of gas around young stars, shells from supernova explosions. But on the scale of entire galaxies, perfect alignment is almost impossible to achieve. Hoag's object defies this logic. The yellow core is positioned almost exactly at the center, with the ring extending outward like a measured circle. It is so precise that one could imagine drawing a line from the nucleus to any point on the ring and finding it equal in length, no matter the direction. For a galaxy created by chance, this degree of balance shouldn't exist. The mystery deepens when we consider how long the galaxy has existed. Galaxies are not static. They evolve, stretch, and shift over billions of years. If Hoag's object had once been circular by accident, the expectation would be that time would slowly distort its shape. Gravitational tugs from nearby objects, internal motion within the ring, or uneven star formation should have warped the circle into something less precise. But even after hundreds of millions, possibly billions of years, the circle remains intact. It seems to defy the natural entropy that dominates cosmic structures. In this sense, Hoag's object is less like a typical galaxy and more like a frozen anomaly, something that has resisted the universe's constant push toward disorder. This is why its symmetry has captured such fascination. It doesn't just look unusual, it appears to mock the randomness of cosmic evolution. Some astronomers have even compared it to a standing wave in physics, a delicate balance of opposing forces that holds its form despite constant motion. But unlike standing waves on Earth, which can be explained by precise equations, Hoag's object offers no straightforward formula. Its existence hints that either an unknown process shaped it into this form, or we are witnessing one of the universe's most extraordinary coincidences. In the vastness of space, perfection is not the norm. Stars are born unevenly, galaxies warp and collide, and randomness reigns supreme. Yet Hoag's object is a reminder that sometimes the universe produces something so precise, so orderly, that it feels less like chance and more like intent. Its perfect circle is not just a curiosity, it is a challenge to everything we think we know about cosmic formation, a symbol of nature's ability to surprise us with patterns that should not exist on such a colossal scale. In order to fully appreciate the uniqueness of Hoag's object, it helps to compare it with the types of galaxies that dominate our understanding of the universe. The majority of galaxies fall into three broad categories: spiral, elliptical, and irregular. Each of these categories has its own formation history, structure, and behavior, all of which follow relatively well understood cosmic principles. Spiral galaxies, like our Milky Way or the Andromeda Galaxy, are characterized by a flattened disk of stars and gas, adorned with swirling arms that wind out from a dense central bulge. These arms are regions of intense star formation, glowing with clusters of young, blue stars, while the core remains populated by older, yellowish stars. Spiral galaxies are dynamic and complex. Their arms can be loosely or tightly wound, their disks warped by gravitational interactions, and their centers sometimes host supermassive black holes that shape their evolution. In contrast, elliptical galaxies are more uniform and spheroidal in shape. They are dominated by older stars, with very little gas or dust left to form new stars, which gives them a smooth, featureless appearance. Irregular galaxies are the wild cards of the universe, chaotic in shape, often distorted by collisions or gravitational interactions, lacking clear symmetry, and displaying star formation in unpredictable regions. In this context, each galaxy type has a recognizable structure, one that astronomers can classify and explain based on well-established physical principles. Hoag's object, however, does not fit into any of these categories. At first glance, one might attempt to force it into the spiral or elliptical molds, but the evidence refuses to cooperate. Its central core resembles an elliptical galaxy only superficially, being composed of older stars with a yellowish hue. But elliptical galaxies do not have the bright, sharply defined rings that Hoag's object boasts. Likewise, one might argue that the galaxy could be a highly unusual spiral seen directly face-on, which could give the illusion of a ring. Yet, spiral galaxies, even when observed from such an angle, rarely display the absolute uniformity and symmetry that define Hoag's object. Spiral arms, even when faint, tend to appear as arcs, with density waves and irregularities that break any sense of perfection. The empty gap between the core and the ring further defies this categorization, as spiral galaxies almost always have some distribution of stars and dust connecting the core to the arms. Irregular galaxies, on the other hand, are so chaotic that their shapes provide no useful point of comparison. Their stars are scattered, their gas clouds uneven, and their overall appearance is anything but a precise circle. By every conventional measure, Hoag's object simply does not belong to the known galactic families. This distinction is not just a matter of aesthetic curiosity, it has profound implications for astrophysics. Galactic morphology, the study of galaxy shapes, is intimately linked to how galaxies form and evolve. Spiral galaxies, for example, form their arms due to the differential rotation of their disks combined with density waves that trigger star formation. Elliptical galaxies often result from mergers or the gravitational collapse of massive gas clouds early in the universe's history. Irregular galaxies frequently owe their shape to collisions, tidal forces, or internal instabilities. When a galaxy fits neatly into one of these categories, astronomers can trace its history, infer its age, and model its future with reasonable accuracy. Hoag's object resists such analysis. Its formation pathway is unclear. Its maintenance of a perfect ring, despite the forces that typically distort galaxies, is inexplicable. And its apparent stability over hundreds of millions of years contradicts expectations based on both spiral and elliptical dynamics. Even more striking is the galaxy's distribution of stellar populations. In a typical spiral, the older stars dominate the central bulge, while younger stars form in the arms, a continuous, overlapping pattern. Elliptical galaxies, conversely, have predominantly old stars with minimal new formation, and irregular galaxies scatter stars of all ages unevenly. Hoag's object, however, exhibits a sharp segregation. The core contains older stars, and the ring is populated exclusively by bright, blue young stars, with a nearly empty void in between. This abrupt boundary is extremely rare. Most galaxies display some form of gradient, a smooth transition from old to young, from dense to sparse. Hoag's object violates this principle entirely. Its structure almost seems to suggest two separate galaxies or stellar systems superimposed upon one another. Yet there is no evidence of a collision that could account for this separation, nor any indications of gravitational turbulence sufficient to maintain such a perfect configuration. The structural oddity of Hoag's object also extends to its size and scale. The ring itself spans tens of thousands of light-years, comparable in scale to the arms of the Milky Way. Yet it is unusually narrow and uniform. Its thickness is consistent around the circumference, and there are no major clumps or irregularities, a stark contrast to the uneven distributions seen even in some of the most symmetrical spiral galaxies. The precision of this cosmic ring stretches the limits of what we understand about gravitational equilibrium and star formation. To maintain such uniformity, the forces governing the ring's motion must be astonishingly finely tuned, something rarely observed in natural galaxies. Even minor perturbations from nearby intergalactic matter, passing stars, or dark matter concentrations should have warped or fragmented the ring over time. Yet it remains intact, a flawless loop of stellar brilliance encircling an isolated older core. Furthermore, the separation between the core and the ring introduces another layer of complexity. In spiral galaxies, stars, gas, and dust form continuous structures from the center outward. In elliptical galaxies, stars are evenly distributed across a spheroidal shape. Irregular galaxies lack any coherent center-to-edge organization. Hoag's object is unlike any of these. Its dark gap, stretching thousands of light-years across, seems almost engineered, an impossible void given the usual distribution of matter in a galaxy. The core and the ring are gravitationally connected, yet the space between them is so empty that it challenges our understanding of how galaxies retain their cohesion and balance. What keeps the ring in place without it collapsing inward or dispersing outward? How did this empty space form without being filled by stars, gas, or dust over billions of years? These are questions that conventional galactic models cannot satisfactorily answer. Even with advances in modern astronomy, Hoag's object continues to stand out as an anomaly. High-resolution imaging from space telescopes has revealed more details, showing clusters within the ring and subtle variations in star brightness. Yet the fundamental problem remains: it does not fit. When astronomers compare it with well-studied galaxies, the differences are glaring. The galaxy is not only structurally alien, but its very existence suggests that nature can produce configurations far beyond the patterns we have catalogued and studied for over a century. Its classification remains tentative. Some place it in the rare category of ring galaxies, but even within that designation, it occupies a special, almost solitary position. Most ring galaxies are formed by collisions or interactions that leave visible scars. Hoag's object shows none. Its ring is smooth, its core perfectly aligned, and its overall shape so refined that some researchers describe it as the perfect galaxy, a model that nature almost never achieves. This exceptional deviation from standard forms has made Hoag's object a centerpiece in debates about galaxy formation. It forces astronomers to reconsider assumptions about how stars can organize on cosmic scales. If galaxies were purely the products of random collisions and chaotic gas dynamics, such an object should be nearly impossible. Yet it exists in all its alien elegance. Studying it offers more than just aesthetic appreciation. It challenges the foundational principles of astrophysics, compelling scientists to explore new ideas about gravitational forces, star formation, and galactic evolution. In a universe dominated by spirals, ellipses, and chaos, Hoag's object stands as a singular testament to the cosmos's capacity for strangeness, precision, and wonder, proving that not all galaxies can be neatly categorized, and that some will forever resist the boundaries we try to impose upon them. One of the earliest and most widely considered explanations for Hoag's object was the possibility that it formed from a galactic collision. In astrophysics, collisions between galaxies are common events. Over billions of years, galaxies drift through space, and their gravitational fields can pull them together, sometimes leading to dramatic encounters. Such collisions often leave behind striking features: tidal tails, arcs of stars, warped disks, and other distortions that tell a story of violent interaction. In the case of Hoag's object, it seemed plausible that perhaps a smaller galaxy had passed directly through the core of a larger one. This could have triggered a density wave, pushing the stars outward and leaving a circular ring in the process. The theory draws analogies to ripples spreading across a pond when a stone is thrown into it. The initial impact disrupts the medium and forms concentric rings. In principle, a galactic collision could have created the bright, uniform ring of blue stars surrounding the yellow core. However, when astronomers examined Hoag's object in greater detail, several inconsistencies with the collision theory emerged. First, most galaxies that have undergone a head-on collision show evidence of chaos, distorted structures, scattered star clusters, and irregular patterns in gas and dust distribution. Hoag's object, in contrast, exhibits almost perfect symmetry. The ring is smooth and uniform, with a sharp, well-defined inner edge, and there are no visible tidal tails or residual debris that would indicate a recent violent interaction. Even advanced imaging, using space telescopes, has failed to reveal the sort of scars one would expect from a catastrophic galactic encounter. In this sense, the galaxy appears too pristine to have been the product of a collision. Another challenge to the collision hypothesis is the age and formation rate of the stars within the ring. Observations suggest that the ring stars are relatively young, forming in clusters that shine with a bright blue hue. If the ring had resulted from a collision hundreds of millions of years ago, astronomers would expect a more mixed stellar population, with some older stars thrown into the ring during the event. The fact that the ring is dominated almost exclusively by young stars implies either a very recent event, which would be statistically unlikely given the precision and symmetry, or an alternative formation mechanism that allowed star formation to be triggered selectively in the ring while leaving the core untouched. Neither scenario is fully supported by current evidence, leaving the collision explanation incomplete. Gravitational dynamics also complicate the collision theory. For a head-on collision to produce a perfect ring like that of Hoag's object, the impact would have had to be almost exactly aligned with the galaxy's center of mass, occurring with precise velocity and angle. In reality, galactic collisions are messy and often result in asymmetrical distortions. The odds of such a perfectly centered impact occurring, producing a flawless ring, and leaving behind an untouched core without any residual disturbances are astronomically low. While not impossible, this level of precision strains credibility and highlights why many astronomers remain skeptical of the collision scenario. Additionally, computer simulations that model galactic collisions and ring formation often show subtle imperfections, slight ripples, clumps, or uneven density distributions that are absent in Hoag's object. These simulations incorporate known physics, including gravity, star formation feedback, and dark matter distributions, yet they fail to reproduce a ring as clean and uniform as what we observe. This discrepancy suggests that, if a collision did occur, it would have to involve conditions or mechanisms that are not yet understood, pointing to gaps in our knowledge about galactic evolution. The absence of nearby galaxies that could have caused such a collision also raises questions. Most ring galaxies formed through interactions can be traced to a companion or intruder galaxy that either triggered the ring or was partially absorbed. Hoag's object, however, appears isolated, with no obvious candidate for the interloper that could have passed through its core. This isolation further undermines the collision hypothesis, as it becomes harder to identify a plausible source for the event. Without evidence of a responsible intruder or traces of gravitational disturbance, the notion of a galactic collision remains speculative at best. Even proponents of the collision theory acknowledge its limitations. While it can conceptually explain how a ring might form around a core, it cannot fully account for the precise symmetry, the empty gap, or the clear segregation of stellar populations observed in Hoag's object. The galaxy's extraordinary perfection and isolation suggests that if a collision did play a role, it would have to be unlike any collision observed elsewhere in the universe. This has led researchers to explore alternative hypotheses, including those involving gravitational resonance or other dynamical processes, which may offer a more plausible explanation for the galaxy's unique appearance. Ultimately, the collision theory is tantalizing because it relies on known cosmic mechanics, gravity, motion, and the effects of impact. But the evidence fails to align perfectly with the reality of Hoag's object. While it cannot be entirely ruled out, the improbability of producing such a flawless, isolated ring through a chaotic collision makes it an incomplete answer. The galaxy continues to defy our attempts to categorize its formation, leaving it as one of the most enigmatic and puzzling structures in the observable universe. Its perfection is so improbable under a collision model that scientists are forced to consider other explanations, perhaps ones that involve processes still beyond our current understanding of galactic dynamics. Another compelling explanation that astronomers have explored is the idea that Hoag's object may have formed through a process known as gravitational resonance. In essence, gravitational resonance occurs when the gravitational forces within a system interact in such a way that they reinforce certain motions and suppress others, creating patterns that can appear surprisingly organized over vast scales. In planetary systems, we see similar phenomena, such as the orbital resonances of moons around Jupiter or Saturn, where gravitational interactions lock objects into harmonious paths. When applied to a galaxy like Hoag's object, the theory suggests that the combined gravitational pull of the central core surrounding stars and possibly dark matter could have sculpted the stars into a circular ring, maintaining their positions through a delicate balance of forces over millions or even billions of years. The idea is appealing because it provides a mechanism that could naturally produce the symmetry we observe, without requiring an improbable collision or an external intruder. Gravitational resonance could, in theory, explain several of Hoag's object's defining features. For one, it accounts for the ring's stability. If stars within the ring are moving along resonant orbits, they would naturally avoid drifting inward toward the core or outward into intergalactic space, remaining confined to a precise circular path. This would also help explain the sharp separation between the core and the ring. The resonance might create a forbidden zone, an area where stellar orbits are unstable and cannot persist, resulting in the empty gap we observe. In other words, the void is not just empty by chance, it may represent a natural consequence of the gravitational dynamics at play. Similarly, resonance could help maintain the ring's uniformity, preventing the clumping or uneven distribution of stars that would typically occur due to localized gravitational instabilities. Despite these theoretical possibilities, the gravitational resonance hypothesis faces significant uncertainties. For one, the precise conditions required to establish such a resonance on the scale of Hoag's object are extreme. The gravitational interactions would need to be finely tuned, with the mass distribution of the core, the ring, and any surrounding dark matter arranged in an almost impossibly precise way. Small deviations in the mass of the core, the velocity of stars, or the distribution of unseen dark matter could destabilize the system entirely. In simulations, researchers have struggled to replicate the near-perfect symmetry of Hoag's object using gravitational resonance alone, suggesting that if this process is responsible, it requires conditions that are extraordinarily rare, perhaps even unique in the observable universe. Furthermore, while resonance could explain the ring's shape and stability, it does not fully account for the distinct difference in stellar populations between the core and the ring. The core contains old, yellow stars, while the ring is dominated by young, blue stars. Resonance can maintain the position of stars, but it cannot generate new stars or dictate the age distribution within the ring. The presence of active star formation in the ring implies additional processes, such as localized gas dynamics, that would need to be finely balanced with the resonant gravitational structure. This introduces a layer of complexity that the resonance hypothesis alone cannot resolve, leaving astronomers to speculate about how multiple mechanisms might have worked in concert to produce such an extraordinary formation. Another point of uncertainty is the origin of the initial conditions required for resonance to form. For resonance to sculpt a ring of this magnitude, the system must have started in a configuration that already favored circular symmetry. How such a configuration came about remains a mystery. Did the galaxy begin as a more conventional spiral or elliptical galaxy, only for its stars to gradually settle into resonant orbits? Or did some other, as yet unknown process arrange the stars and mass in a way that allowed resonance to occur? Without a clear understanding of the galaxy's early history, gravitational resonance remains a plausible yet unproven explanation. Observations of other ring galaxies provide some context, but also highlight the limitations of the resonance theory. Other known ring galaxies are often messy and irregular, many formed by collisions or interactions, and none display the same level of symmetry and isolation as Hoag's object. If gravitational resonance were a common mechanism for creating rings on galactic scales, we would expect to see more examples with similar precision. The apparent rarity of Hoag's object suggests that either the conditions for resonance are extraordinarily rare, or that additional unidentified factors were involved in its formation. In spite of these challenges, the gravitational resonance hypothesis remains one of the more attractive explanations because it relies on known physics rather than invoking improbable coincidences or hypothetical processes. It offers a framework for understanding how such a precise ring could persist over cosmic timescales, and it emphasizes the role of the galaxy's own internal forces in shaping its structure. Yet, the gaps in the theory highlight the limitations of our current understanding of galactic dynamics. Hoag's object continues to resist categorization, serving as a reminder that even processes that seem theoretically plausible can fall short when confronted with the complexity and subtlety of real cosmic systems. Ultimately, the resonance idea illustrates both the ingenuity and the frustration of astrophysics. It is a theory that makes sense in principle, that offers a potential mechanism for maintaining order amidst chaos, yet remains unverified because the galaxy defies the models used to test it. The mystery of Hoag's object is amplified by this uncertainty. It is a structure that could, in theory, be explained, but in practice, still challenges astronomers to reconcile its perfection, symmetry, and dynamism with the laws of physics as we currently understand them. For now, gravitational resonance is a tantalizing possibility, one that may someday provide part of the answer, but like so many aspects of this galaxy, it does not offer a complete resolution. One of the most striking features of Hoag's object is its brilliant blue ring, which is not merely a decorative halo, but a vibrant cradle of new star formation. These hot blue stars are relatively young in cosmic terms, burning with intense energy and living fast, short lives that often last only a few million years before exhausting their fuel and ending in supernovae. Their presence is a clear sign that Hoag's object is not a dormant or dead galaxy, but a system still very much alive, continuing to create new stars even as its core remains dominated by ancient yellow stars. The vivid contrast between the energetic youth of the ring and the quiet maturity of the core is part of what makes this galaxy so visually and scientifically compelling. It is a simultaneous portrait of cosmic past and present, frozen in a single, almost impossibly ordered formation. Star formation in galaxies typically occurs in regions dense with gas and dust, known as molecular clouds. Within these clouds, gravitational collapse triggers the birth of stars, igniting nuclear fusion in their cores. In Hoag's object, the blue ring appears to be one enormous, continuous zone of star formation. Observations suggest that the ring is packed with hot, massive stars, each one thousands of times brighter than our Sun, their ultraviolet light illuminating the surrounding space. This activity implies that the galaxy has retained, or perhaps accumulated, a sufficient supply of interstellar gas in the ring to sustain star formation over extended periods. What is puzzling, however, is how this star-forming material is confined to such a sharply defined ring without spilling inward toward the core or outward into the surrounding void. Most galaxies with active star formation display more dispersed patterns. Spiral arms have clumpy star-forming regions. Irregular galaxies host scattered stellar nurseries, and even ring galaxies formed by collisions often exhibit irregularities in their star-forming rings. Hoag's object, by contrast, maintains a smooth, continuous, almost mathematically precise ring of stellar creation. The intensity of star formation in the ring has profound implications for understanding the galaxy's dynamics. Hot, massive stars exert strong radiation pressure and stellar winds, which can blow surrounding gas away, disrupt further star formation, or even trigger new bursts of collapse in nearby regions. In the ring of Hoag's object, these processes seem balanced in a remarkable equilibrium. The ring sustains ongoing star formation without becoming too clumpy or dissipating entirely. The forces at play must be finely tuned, perhaps influenced by the gravitational effects of the core, the ring's own mass, or even unseen dark matter shaping the orbits and density of the stars. It is a delicate choreography, where the birth of stars continues over millions of years in a structure that remains coherent and circular. Another striking feature of the blue ring is its uniformity. The color alone indicates that the stars are young and massive, typically less than a few 100 million years old, which is extremely young compared to the age of the galaxy itself. This suggests a wave of star formation that occurred almost simultaneously around the ring, or at least a process that promotes uniform stellar birth along its circumference. This level of consistency is unusual. In most galaxies, star formation tends to be patchy, with certain regions more active than others due to variations in gas density, turbulence, or prior supernova activity. Hoag's object defies this expectation, presenting an almost seamless band of young stars circling the older core. The ongoing star formation also hints at the galaxy's evolutionary timeline. The central core, with its older yellow stars, likely formed long ago, perhaps billions of years before the ring came into existence. The ring itself may have been triggered later, either by internal dynamics such as gravitational resonance, by the infall of gas into a preferred orbital path, or by some other mechanism that funneled star-forming material into the periphery of the galaxy. Regardless of the precise cause, the result is a galaxy that simultaneously showcases two distinct generations of stars in remarkable proximity: an aged core of ancient stars and a youthful ring teeming with new life. This duality is rare, and it provides a living laboratory for astronomers to study the processes that regulate star formation on a galactic scale. Observational data also indicate that the ring's stars are not forming in isolation. Many of these massive blue stars are found in clusters bound together by gravity and likely formed from the same molecular clouds. These clusters can later disperse, seeding the galaxy with smaller groups of stars, but within the ring, they appear to maintain coherence, further contributing to the visual and structural regularity of the formation. Their ultraviolet emissions illuminate the surrounding gas, highlighting the contours of the ring and making it visible even across hundreds of millions of light-years of intergalactic space. This glowing halo of youthful stars is what gives Hoag's object its most iconic and otherworldly appearance, distinguishing it from every other galaxy astronomers have catalogued. The presence of active star formation in the ring also raises questions about the galaxy's long-term stability. Massive stars evolve rapidly, producing supernovae that inject energy and heavy elements into their surroundings. Over time, this could disrupt the delicate balance of the ring or alter its orbital dynamics. Yet the ring remains sharply defined and continuous, suggesting that either the processes governing the ring are highly efficient at maintaining stability, or that it is being replenished with gas from some source, possibly the intergalactic medium or residual material from the galaxy's formation. Understanding how the ring sustains its star formation while preserving its perfect shape continues to puzzle astronomers and underscores just how extraordinary Hoag's object is. Ultimately, the hot blue stars of Hoag's object are more than just a visually stunning feature. They are evidence of a galaxy that is alive and dynamic, despite its alien and seemingly improbable structure. They highlight the complex interplay between gravity, gas dynamics, and stellar evolution, all working together to produce a ring of dazzling young stars that circles an older, serene core. In this way, Hoag's object is both a relic of the past and a factory of the present, a cosmic paradox where two distinct stellar populations coexist in near-perfect harmony, offering a glimpse into processes of star formation that remain only partially understood. Its vibrant ring serves as a luminous testament to the galaxy's ongoing vitality and reinforces the sense that, in Hoag's object, the universe has created something truly exceptional, a place where the creation of new stars is as much a part of its mystery as its impossible symmetry and enigmatic structure. One of the most perplexing aspects of Hoag's object is the vast, seemingly barren expanse that separates its luminous blue ring from the golden core, a dark gap that stretches tens of thousands of light years across, almost perfectly uniform in width. Unlike most galaxies, where stars, gas and dust are distributed more or less continuously from the center outward, Hoag's object exhibits a sharp, striking division. In a typical spiral galaxy, for instance, the density of stars gradually decreases as one moves from the bright core into the arms, and interstellar gas often fills the regions between them, supporting ongoing star formation and linking the central bulge to the outer regions. Elliptical galaxies, though smoother, still display gradients in star density without such abrupt voids. Even in other ring galaxies, which are often the result of collisions, the gaps between core and ring tend to be partially filled with stars or gas. Hoag's object, by contrast, presents a near-empty void, as if some unseen hand cleared out everything between the core and the ring, leaving a hauntingly pristine circle of darkness. This emptiness raises immediate questions about the galaxy's formation and dynamics. What could have cleared, or perhaps prevented, the accumulation of stars in such a vast region? One possibility is that the gravitational forces within the galaxy have created a stable orbital zone where stars cannot persist. If the core exerts a strong enough gravitational influence, combined with the mass of the ring, certain regions might become dynamically unstable, causing any stars or gas in the intervening space to either collapse inward toward the core or migrate outward into the ring. Essentially, the gap could represent a forbidden zone, a region of orbital instability where matter cannot remain for long periods of cosmic time. While this theory is plausible, it does not fully explain the uniformity and precision of the void. Most dynamical gaps in galaxies are irregular, warped, or somewhat clumpy. Yet here, the emptiness is astonishingly clean. Another possibility involves the galaxy's formation history. If the ring formed from a wave of star formation, propagating outward from the core, it could have swept up or expelled material from the intermediate space, leaving behind a dark void. In this scenario, the gap is not a passive feature, but an active consequence of the processes that built the ring itself. Yet the absence of residual gas, dust, or star clusters challenges even this explanation. Observations reveal little to no material in the gap, not even traces of faint stars or diffuse gas, which would normally linger after such a wave. It is almost as if the space between the core and the ring was never populated at all, defying the gradual, messy processes that usually govern galactic evolution. The size of the void adds to its mystery. Stretching possibly tens of thousands of light years, the gap is immense on a human scale, large enough to contain an entire dwarf galaxy. In a universe where matter tends to coalesce under gravity, leaving such a region entirely empty is difficult to reconcile with known physical principles. Gravity should have pulled material inward toward the core or outward into the ring, yet the region persists as a stable, seemingly uninhabitable space. Its maintenance over hundreds of millions of years suggests that some long-term mechanism is preventing matter from populating the gap, but the exact nature of that mechanism remains elusive. This emptiness also enhances the visual and symbolic impact of Hoag's object. The contrast between the glowing yellow core and the brilliant blue ring is made all the more dramatic by the void, creating a sense of isolation and precision that is rarely seen in natural structures. The human eye perceives the ring not just as a band of stars, but as a halo suspended in space, circling a core as if floating in a vacuum. From a scientific perspective, this gap is a clue to the galaxy's formation and stability, offering a rare window into the dynamics of an unusually organized system. Understanding why it is so empty could help unlock the secrets of ring galaxy formation, stellar migration, and gravitational orchestration on cosmic scales. Some theories even speculate that the gap might have been formed by processes that we do not yet fully understand, possibly involving dark matter. If an unusual concentration or distribution of dark matter exists within the galaxy, it could influence the gravitational potential in ways that prevent stars or gas from settling in certain regions. While this remains speculative, it underscores the broader point that Hoag's object challenges conventional thinking. The rules that govern most galaxies do not seem to apply cleanly here. The gap is not simply an absence of matter, it is a structural statement, a manifestation of forces that have sculpted the galaxy into a configuration that seems almost deliberate. Even in the context of other ring galaxies, Hoag's object's void is exceptional. Many known ring galaxies have gaps, but they are often irregular, warped, or populated with scattered remnants of stars and gas. Hoag's object's gap is uniform, circular, and devoid of any significant material, suggesting a level of precision and stability far beyond what is typically observed. This makes it an ideal subject for studying the dynamics of ring formation, the interplay between gravitational forces and star formation, and the long-term stability of isolated structures in space. The empty space between the core and the ring is thus more than a mere curiosity. It is a fundamental characteristic that defines Hoag's object. It highlights the galaxy's defiance of conventional galactic evolution, presents a profound challenge to astrophysicists trying to model its formation, and contributes to its overall aura of cosmic strangeness. The void is a silent yet powerful clue, a reminder that the universe can produce structures that are both beautiful and puzzling, and that Hoag's object continues to guard secrets about the forces that shape galaxies on the largest scales. At the heart of Hoag's object lies its enigmatic yellow nucleus, a dense, luminous sphere that presents a striking contrast to the brilliant, youthful blue ring encircling it. This core is composed predominantly of older red and yellow stars, the remnants of generations that have long exhausted the raw material needed for further stellar birth. The color alone is a telltale indicator of age. Yellow stars, cooler and less massive than the hot blue stars in the surrounding ring, suggest a population that has existed for billions of years. A cosmic elder standing in quiet opposition to the vibrant, frenetic life of the ring. Its smooth, almost featureless appearance bears a resemblance to elliptical galaxies, which are typically characterized by such a homogeneous distribution of aged stars and minimal interstellar gas. However, the presence of the sharply defined ring around it makes this core unique. In most elliptical galaxies, one would not expect to see such an abrupt, isolated halo of young stars. The central core's composition and structure hint at its history, possibly serving as a relic of a galaxy that existed before the ring came into being. If the core was indeed an elliptical galaxy in the past, it may have undergone internal processes or external interactions that eventually triggered the formation of the surrounding ring. The juxtaposition of old and new stars is unusual. The core seems calm, settled, and mature, while the ring is a region of active, dynamic star formation. This stark difference raises intriguing questions about the galaxy's evolution. How did the core maintain its stability while a vigorous star-forming ring developed so dramatically around it? In typical galaxy models, interactions or disturbances that trigger ring formation would likely disrupt the central core to some degree, yet Hoag's object exhibits a serene, undisturbed nucleus, further deepening the enigma. Observations of the core reveal additional subtleties. Its luminosity is intense, concentrated, and symmetric, reinforcing the overall circular perfection of the galaxy. Unlike many elliptical galaxies, which may appear elongated or slightly irregular due to gravitational influences or past mergers, Hoag's object's nucleus is nearly a perfect sphere, mirroring the symmetry of the surrounding ring. This alignment suggests a gravitational balance between the core and the ring, as if the central mass exerts just enough influence to maintain the ring's orbital path without allowing it to collapse inward. The sharp boundary between the core and the gap adds to the impression that the core is not only a relic of an older galaxy, but also an active stabilizing agent within this cosmic structure. The contrast between the yellow core and the blue ring is not just a visual spectacle, but also a clue to the galaxy's life cycle. The core represents the ancient, settled population of stars that formed in the early universe, long before the ring of young stars emerged. The blue ring, in contrast, tells a story of ongoing star formation, fueled by gas that either persisted in orbit around the core or was acquired later. This dichotomy is unusual. In most galaxies, star populations are more gradually distributed, with age gradients rather than abrupt separations. The near-perfect segregation in Hoag's object implies a highly organized formation process, whether through gravitational resonance, a unique accumulation of gas, or some mechanism not yet fully understood. Spectroscopic studies of the core provide further insights. The yellow stars indicate a lower rate of stellar activity, with minimal supernovae or energetic events compared to the high-mass stars in the ring. This lack of turbulence may contribute to the ring's ability to maintain its shape. A stable, calm core reduces gravitational disturbances that could otherwise warp or destabilize the surrounding ring. Yet even with this understanding, the coexistence of such a tranquil nucleus with a highly active, precise ring remains an unusual combination, rarely seen in other galaxies. The core's density is another intriguing factor. While it appears compact, its mass is significant enough to influence the dynamics of the ring. The gravitational pull of the nucleus likely helps maintain the ring's orbit, providing a centripetal anchor around which the younger stars can revolve. This relationship underscores the delicate balance of forces within Hoag's object. The core's mass ensures the ring's stability, while the ring's star formation does not interfere with the core's equilibrium. Such a perfect harmony of age, composition, and gravitational influence is extraordinarily rare in galactic structures. Moreover, the nucleus may hold secrets about the galaxy's origin. If it is indeed an older elliptical galaxy, its presence suggests that Hoag's object is not a primordial structure, but rather the result of a complex evolutionary process. The core could have served as a seed around which the ring later developed, whether through the outward propagation of star-forming material, gravitational resonance effects, or an external event that left the core largely untouched. Understanding the nucleus's properties, its mass, composition, and kinematics, offers a window into the history of Hoag's object, providing essential clues about the mechanisms that allowed such a perfect ring to form around it. In visual terms, the yellow core provides a sense of grounded permanence against the ephemeral, energetic brilliance of the blue ring. It is a cosmic juxtaposition of age and youth, stillness and activity, providing a tangible representation of time on galactic scales. In Hoag's object, The central nucleus is not merely the heart of the galaxy. It is both anchor and witness, an ancient presence encircled by the vitality of a younger generation, maintaining the balance that has allowed this extraordinary, enigmatic galaxy to persist in near-perfect form. As astronomers have peered deeper into Hoag's object with high-resolution telescopes, a startling discovery has emerged. Through the ring and the central gap, faint traces of yet another ring-like structure appear in the background. When observed under precise imaging conditions, this smaller ring galaxy seems almost to nest inside the larger structure, visible through the transparent void that separates the primary ring from the nucleus. The effect is not simply a projection of stars or a lensing artifact. Detailed analysis suggests that there really is a second, distant galaxy aligned along our line of sight, giving the impression of a galaxy within a galaxy. The coincidence is remarkable. Space is vast, and the odds of such a perfect alignment happening purely by chance seem staggeringly low. Yet here it is, as if the cosmos has intentionally staged a visual echo of the primary galaxy's own structure. This secondary ring adds layers of mystery to Hoag's object. Not only does the main galaxy defy conventional models with its pristine symmetry and clear segregation of stellar populations, but now the apparent presence of a background ring introduces the possibility of a deeper connection between structures on vastly different scales. Could the alignment be purely coincidental, a serendipitous optical illusion produced by our perspective from Earth? While this is statistically plausible, astronomers routinely observe multiple galaxies along the same line of sight. The nearly concentric positioning relative to the core and ring of Hoag's object amplifies the sense of intentionality, raising questions about whether we are witnessing a natural phenomenon or something more profound. Gravitational lensing is one phenomenon that could explain part of this effect. Massive galaxies or clusters can bend the light of background galaxies, sometimes producing arcs, rings, or distorted images known as Einstein rings. However, in the case of Hoag's object, the observed secondary ring does not perfectly match the expected distortions from lensing alone. It maintains a relatively regular structure, suggesting it is an independent galaxy rather than merely a stretched image of background light. This observation complicates the narrative. We see what looks like another ring galaxy precisely framed within the foreground galaxy's ring, but it is unlikely to be caused purely by gravitational bending of light. If it is indeed a separate galaxy positioned behind Hoag's object, it presents a unique opportunity to study interactions between foreground and background structures. Although there is no evidence that the two galaxies are physically interacting, they are almost certainly separated by vast distances along our line of sight. Their alignment could provide clues about the distribution of matter in the universe, the structure of the cosmic web, and the statistical likelihood of such rare configurations. In cosmology, instances like this are often used to test models of galaxy distribution and the probability of random alignments. Hoag's object, therefore, serves not only as a singular cosmic mystery in its own right, but also as a lens, both literally and figuratively, through which we can examine the broader architecture of the universe. The presence of a secondary ring galaxy also invites speculation about symmetry on a cosmic scale. Hoag's object itself is nearly flawless in its circularity, and now, aligned within its gap, another ring appears, creating an almost recursive pattern. A galaxy with a ring, within which we see another ring galaxy. This layering evokes philosophical and scientific questions about whether the universe exhibits self-similar structures at multiple scales, or whether this is simply an extraordinary coincidence amplified by our observational perspective. Such coincidences are not impossible, but their improbability magnifies the wonder and raises the stakes for astronomers attempting to understand what they are seeing. From an observational standpoint, Detecting this inner galaxy requires careful filtering to separate its light from the halo of the main ring. The blue ring of Hoag's object is so luminous and expansive that any background structures can be easily overwhelmed or obscured. Advanced imaging techniques, including long-exposure photography, adaptive optics, and spectral analysis, have made it possible to distinguish the secondary ring from the foreground stars, confirming that it is not part of Hoag's object itself. These observations also allow astronomers to estimate the relative distance of the background galaxy and its approximate redshift, further clarifying that this is a separate entity existing billions of light-years away, yet appearing nested within the foreground ring due to the sheer chance of alignment. Even though the secondary ring is likely a distant, unrelated galaxy, its presence profoundly affects the interpretation of Hoag's object. It reinforces the idea that this galaxy exists within a dynamic, layered universe where chance alignments can produce patterns of surprising symmetry. It also underscores the importance of perspective in astronomy. What appears to be a single, unified structure may in fact be a composite of multiple systems along a line of sight, challenging our assumptions about cosmic organization. Hoag's object, therefore, becomes not only a subject of study for its internal mysteries, but also a stage on which the universe demonstrates its to surprise, to juxtapose unrelated structures in ways that appear almost purposeful, and to present phenomena that seem to echo the galaxy's own improbable perfection. The apparent galaxy within a galaxy effect is more than a curiosity. It is a visual reminder that our universe is full of coincidences, alignments, and structures that challenge our expectations. Whether a cosmic quirk or a clue to deeper patterns, the nested ring evokes awe and amplifies the sense of mystery surrounding Hoag's object. It invites reflection on the scale of the cosmos, the probabilities that govern cosmic configurations, and the ways in which our observations of distant galaxies can reveal layers of complexity we might never have imagined. The universe, in this sense, is not just a collection of stars and matter. It is a canvas capable of producing astonishing coincidences that mirror the extraordinary structure of Hoag's object itself. Hoag's object is not only remarkable for its symmetry and unusual structure, but also for its immense scale. Spanning roughly 100,000 light-years in diameter, it is comparable in size to our own Milky Way, a galaxy teeming with hundreds of billions of stars, complex spiral arms, and diffuse gas clouds. Yet despite its comparable dimensions, Hoag's object appears entirely alien, as if it were drawn from a cosmic imagination, rather than formed through the processes that shape ordinary galaxies. Where the Milky Way exhibits sprawling, winding arms and a thick, uneven halo, Hoag's object presents a near-perfectly circular ring surrounding a smooth, luminous core, with an empty void in between that enhances the sense of alien precision. Its scale magnifies its oddity. Such perfection is difficult to appreciate fully until one realizes that this is not a miniature or localized feature, but a structure that stretches across an expanse of space equal to the distance between our Sun and the edge of the Milky Way. Understanding the scale of Hoag's object also emphasizes the challenges it presents to conventional astrophysics. Galaxies of this size generally contain enormous amounts of gas, dust, and stars, each influenced by complex gravitational interactions, collisions, and rotational dynamics. The fact that Hoag's object has maintained a ring so uniform and sharply defined over such a vast distance is extraordinary. Across tens of thousands of light-years, small gravitational perturbations, such as passing stars, dark matter clumps, or intergalactic gas flows, would normally create ripples, asymmetries, or distortions. Yet observations show a ring of stunning continuity and precision, indicating that some combination of forces has preserved its structure with extraordinary fidelity. Its sheer size makes this even more impressive. A deviation of even a few thousand light-years would be noticeable, yet the ring's edge remains smooth and unbroken. The massive scale also allows us to contextualize the energetic processes occurring within Hoag's object. The young, hot blue stars in the ring are distributed across an expanse comparable to the Milky Way, meaning that the star formation activity is happening on a galactic scale rather than being localized to small clusters. This implies a remarkable coordination in the conditions that allowed gas clouds to collapse into stars along such a wide circumference, all while leaving the intervening gap empty and the core undisturbed. The scale amplifies the improbability of chance formation, suggesting that whatever mechanisms created Hoag's object, whether resonance, past interactions, or some other process, were capable of orchestrating stellar activity with cosmic precision over an extraordinary distance. Another aspect of its scale is its relationship to light and observation. At approximately 600 million light-years away, the photons we detect from Hoag's object began their journey long before humans even existed, traveling across the vastness of space to deliver this image of cosmic perfection. The sheer distance means that we are observing not only a massive structure, but also a snapshot from hundreds of millions of years in the past. The scale, therefore, is not only spatial, but temporal. We are seeing a galaxy that has maintained its unusual configuration for vast stretches of cosmic time, raising questions about its stability and the processes that allow it to retain such symmetry over eons. Compared to the Milky Way, Hoag's object is deceptively simple in appearance, but extraordinarily complex in implication. While our galaxy's spiral arms and central bulge exhibit the result of billions of years of dynamical interactions, Hoag's object seems almost designed in its minimalism: a luminous core, a vast empty void, and a brilliant ring. Its scale transforms what might seem like a visual curiosity in a smaller system into a cosmic paradox. Maintaining such order across 100,000 light-years challenges our understanding of gravitational equilibrium, star formation, and galactic evolution. For astronomers, its scale magnifies every question about origin, formation, and stability, making even minor irregularities, or the lack thereof, scientifically significant. The alien appearance of Hoag's object at this scale also inspires awe, because it emphasizes how unique it is among known galaxies. Even among ring galaxies, which themselves are rare, none display this combination of size, symmetry, and isolation. The Milky Way, with all its complexity, looks comparatively messy and chaotic. Hoag's object appears as a cosmic jewel, carefully balanced and eerily precise, a structure that could easily be mistaken for an artificial creation, if not for the evidence of natural astrophysical processes. Its scale reinforces the notion that the universe is capable of producing structures that are both vast and remarkably ordered, defying the randomness that normally governs galactic morphology. Ultimately, the scale of Hoag's object is central to its mystique. Stretching across 100,000 light-years, it is a structure that dwarfs human comprehension, yet it achieves a level of symmetry and clarity that seems almost impossible in the chaotic universe. Its size forces astronomers to confront the limitations of current models, as any proposed formation mechanism must account not only for the shape, but also for the extraordinary stability and uniformity across an immense cosmic canvas. In this sense, Hoag's object is both massive and precise, familiar in its dimensions, yet completely alien in appearance, a galaxy whose scale magnifies its enigma and cements its status as one of the most extraordinary cosmic structures ever observed. Hoag's object stands as a stark challenge to conventional astrophysics, primarily because its structure does not align with established models of galactic formation and evolution. Standard theories suggest that galaxies grow and shape themselves through a combination of gravitational collapse, rotational dynamics, and interactions with other galaxies. Spiral galaxies, for instance, form through the gradual winding of material into arms due to angular momentum. Elliptical galaxies result from mergers that randomize stellar orbits, producing a smooth, featureless distribution. And irregular galaxies emerge from chaotic interactions or insufficient gravitational cohesion. Each of these models predicts a certain level of irregularity or gradation in stellar distribution. Yet Hoag's object defies these expectations entirely. Its near-perfect ring, isolated central core, and the empty gap between them appear almost engineered, a configuration that current astrophysical principles struggle to reproduce through natural processes alone. One of the core problems in reconciling Hoag's object with known physics is the simultaneous existence of extreme symmetry and active star formation. While theoretical models can account for ring-like formations in galaxies, often through collisions, resonance, or accretion of gas, none of these processes naturally produce a structure that maintains a flawless circle across 100,000 light-years for hundreds of millions of years while still sustaining vigorous, uniform star formation along the ring. Collisional ring galaxies tend to be messy, with irregular edges and uneven stellar populations. Resonance-driven rings require incredibly precise mass distributions that are statistically improbable. And gas accretion scenarios usually yield more diffuse or uneven structures. The combination of factors that make Hoag's object both orderly and active simply does not fit comfortably into any existing framework. Another issue lies in the empty gap between the core and the ring. As previously noted, most galaxies exhibit a continuous or gradually declining distribution of stars and gas from center to periphery. The gap in Hoag's object is extraordinarily clean and uniform, spanning tens of thousands of light-years with virtually no detectable matter. Current models struggle to explain how a galaxy could naturally expel or avoid accumulating material in such a vast region, while simultaneously forming a dense, star-rich ring outside of it. Any perturbation, gravitational anomaly, or external influence would typically introduce irregularities. Yet Hoag's object maintains a precision that seems to ignore the chaotic forces that shape nearly every other galaxy observed. This defiance of typical galactic physics is one of the reasons why it remains a subject of fascination and intense study. The contrast between the old yellow core and the young blue ring adds yet another layer of complexity. In most galaxies, stellar populations show more gradual age gradients. Older stars dominate the center, with younger stars appearing further out, but rarely in such sharply defined, segregated regions. Hoag's object presents an almost binary distribution, a completely mature, stable nucleus surrounded by a ring of vigorous, newly formed stars, with the intervening space entirely devoid of stars. Such a pattern implies a formation mechanism that can preserve long-term stability while initiating a precisely orchestrated wave of star formation, a combination that defies the typical evolutionary trajectories predicted by current astrophysical models. Furthermore, the galaxy's isolation complicates matters. Many peculiar galactic structures are the result of interactions with nearby galaxies. Tidal forces, mergers, and collisions often sculpt irregular shapes, trigger star formation, and produce rings or arcs. Hoag's object, however, appears relatively isolated, with no nearby massive galaxy to explain its unique morphology. Its structure cannot easily be attributed to external influences, suggesting that the mechanisms responsible for its formation and stability are intrinsic to the galaxy itself. This isolation makes it a cosmic anomaly, It is neither the product of collisions nor typical accretion patterns, placing it outside the predictive power of most galactic evolution theories. Even gravitational models struggle to account fully for Hoag's object. While the forces between the core, the ring, and any dark matter halo could theoretically maintain stability, achieving the near-perfect circular symmetry requires an extraordinary degree of fine-tuning. Small perturbations in mass distribution, stellar velocities, or dark matter density could distort the ring over millions of years, yet the observed ring shows little evidence of such deformation. This suggests either an extraordinarily rare natural configuration or an unknown mechanism that reinforces the symmetry, a factor that modern physics has yet to identify or simulate convincingly. Hoag's object also challenges our understanding of star formation at large scales. The uniformity and intensity of the ring's stellar population require a gas reservoir that is both coherent and stable, able to collapse into new stars evenly across tens of thousands of light-years. Current models of galaxy evolution predict that star formation on such scales should be more stochastic, influenced by turbulence, local density variations, and feedback from supernovae. The fact that Hoag's object maintains such coordinated star formation in a perfect ring indicates a level of regulation and balance that is not predicted by conventional theory. In essence, Hoag's object is a living paradox in the realm of astrophysics. Every feature, the perfect ring, the empty gap, the contrasting stellar populations, the scale of the galaxy, and its relative isolation, presents a direct challenge to established models of galactic evolution. It is a reminder that while physics provides a framework for understanding the universe, nature sometimes produces structures that exceed our expectations and defy easy explanation. Each observation of Hoag's object forces astronomers to reconsider assumptions, test new hypotheses, and confront the possibility that some cosmic phenomena may remain outside the reach of current theory. In this way, Hoag's object is not just a galaxy, it is a puzzle, a provocateur, and a testament to the limits of our understanding, leaving astrophysicists both awestruck and humbled by the ingenuity of the universe. True ring galaxies are among the rarest and most enigmatic structures in the known universe, making Hoag's object a particularly extraordinary example of cosmic architecture. While astronomers have catalogued millions of galaxies, only a small fraction exhibit the sharply defined ring morphology that distinguishes systems like Hoag's object. Even within this small subset, few display the combination of symmetry, isolation, and clarity seen here. Most ring galaxies form as a result of dramatic interactions, collisions or close flybys that trigger radial waves of star formation. But such interactions tend to leave scars, distortions, or irregularities in the resulting ring. Hoag's object, in contrast, appears pristine, as if it has achieved perfection without the violent disruptions that typically accompany ring formation. Its rarity is not just a matter of chance, but a reflection of the delicate conditions required to produce and maintain such a structure. Ring galaxies themselves have been a subject of fascination since their discovery. Systems like the Cartwheel Galaxy demonstrate the chaotic processes that can create a ring. A smaller galaxy plunges through a larger disk galaxy, sending out waves of star formation, and often producing a ring punctuated with clumps and asymmetries. These rings are temporary in cosmic terms, dissipating or evolving into other morphologies over millions of years. In comparison, Hoag's object seems remarkably stable, with a smooth, continuous ring and an enduring gap between the core and the ring. Its longevity and structural precision elevate it above the already rare class of ring galaxies, highlighting just how unusual it is in both form and behavior. Part of the rarity stems from the specific conditions required for ring formation. Galaxies need a carefully balanced distribution of mass, angular momentum, and interstellar gas to produce a coherent ring without collapsing inward or dispersing outward. Even small deviations in these factors can prevent a ring from forming at all or result in irregular, patchy structures. Hoag's object's near-perfect circularity, uniform star formation in the ring, and pristine central void suggest that it occupies an extraordinarily narrow range of parameters that most galaxies simply do not achieve. This precise orchestration of forces across tens of thousands of light-years underscores why such galaxies are exceptional rather than commonplace. Furthermore, the rarity of true ring galaxies is amplified when considering the isolation of Hoag's object. Many known ring galaxies exist in dense clusters or environments where interactions with neighbors are frequent, yet Hoag's object shows little evidence of a recent collisional event or nearby massive companions. This isolation implies that whatever processes formed and maintain the ring are intrinsic rather than externally driven, which is highly unusual. Most ring galaxies owe their structure to violent, unpredictable encounters. A system that appears so perfectly organized without obvious external influence is therefore exceedingly rare in both mechanism and outcome. The combination of structural perfection, active star formation, and stability over vast distances makes Hoag's object not only rare, but also scientifically invaluable. Astronomers studying this galaxy gain insight into the dynamics of ring formation, stellar evolution in isolated environments, and the balance of gravitational forces needed to maintain such symmetry. Its uniqueness ensures that it stands as a benchmark against which other ring galaxies can be compared, offering clues about the limits of natural galactic design and the conditions under which extreme order can arise in the cosmos. Hoag's object's rarity also has implications for observational astronomy. Because so few galaxies exhibit this morphology, each instance becomes a precious laboratory for testing models of galactic dynamics and evolution. Unlike more common spirals or ellipticals, which provide abundant examples for statistical analysis, ring galaxies are rare enough that individual cases, particularly those as extraordinary as Hoag's object, can dramatically influence our understanding of galactic behavior. Every observation adds significant value, contributing to hypotheses about resonance, gravitational stability, and star formation mechanisms that might otherwise remain speculative. In a universe filled with billions of galaxies, the existence of something as visually and structurally extraordinary as Hoag's object is a powerful reminder of the diversity of cosmic forms. Its rarity is not merely a statistical curiosity, it reflects the finely tuned combination of conditions required to produce such perfection. It is a galaxy that stands out not only for what it is, but also for how few others like it exist, marking it as one of the most exceptional and mysterious objects known to modern astronomy. For scientists and enthusiasts alike, Hoag's object is more than just a ring galaxy. It is a testament to the universe's ability to create order and beauty in an otherwise chaotic cosmos. The astonishing symmetry and precision of Hoag's object inevitably raise questions about whether its formation is purely the result of cosmic chance, or if some underlying mechanism, or even principle, guided its creation. At first glance, the galaxy appears almost artificially sculpted. A perfect yellow core, a nearly flawless ring of bright blue stars, and a void in between that stretches tens of thousands of light-years with minimal disruption. The regularity of these features challenges our intuitive understanding of how galaxies form. In the chaotic environment of the universe, where interactions, gravitational perturbations, and turbulent gas dynamics dominate, one would expect galaxies to emerge with irregularities, clumps, and asymmetries. Yet Hoag's object appears organized in a way that is so strikingly orderly that it invites speculation beyond conventional astrophysics. Some astronomers argue that its perfection could be explained as an extraordinary cosmic coincidence. Given the vast number of galaxies in the universe, potentially in the hundreds of billions, rare configurations are statistically inevitable. In this view, Hoag's object is simply one of those improbable alignments where the combination of angular momentum, mass distribution, gas density, and star formation conditions happen to converge in just the right way to produce an almost ideal ring galaxy. Over billions of years, the galaxy would have survived precisely because it occupies a dynamically stable configuration, allowing it to maintain its structure while more chaotic systems evolved or disintegrated. The design we perceive may simply be the human brain's tendency to recognize patterns, amplified by the galaxy's visual clarity and symmetry. Yet many scientists remain unconvinced that pure chance is a sufficient explanation. The level of coordination required to produce Hoag's object, particularly the uniformity of the ring, the complete emptiness of the gap, and the stability of the central core, suggests that some self-organizing process may be at work. Hypotheses have been proposed involving gravitational resonance, in which the core and the surrounding mass distribution interact in such a way that stars naturally migrate into a ring-like orbit, while leaving the intermediate space nearly empty. This would imply that physical laws, rather than random chance alone, guided the galaxy toward this particular configuration. However, while such resonance models are mathematically plausible, they have not yet been observed to produce structures with the extreme perfection seen in Hoag's object, leaving the question unresolved. Another angle considers the role of initial conditions in the early universe. Perhaps Hoag's object formed from a highly symmetrical collapse of a proto-galactic cloud, with angular momentum distributed in a precise manner that favored ring formation. This scenario relies on an unlikely confluence of factors: a centrally concentrated mass for the core, sufficient gas at the periphery to form a coherent ring, and an absence of nearby perturbing forces that could disrupt the emerging structure. While physically possible, the rarity of Hoag's object indicates that such conditions must be exceptionally uncommon, highlighting why few galaxies resemble it even among the relatively rare class of ring galaxies. The idea of an unknown cosmic mechanism also finds traction among some researchers and speculative theorists. Could there be aspects of galactic physics or dark matter interactions that are not yet fully understood, capable of producing such extraordinary order? Perhaps feedback processes from the core, magnetic fields, or the distribution of invisible mass in the halo could subtly guide star formation into the observed configuration. Though purely hypothetical at this stage, these possibilities reflect the broader reality that Hoag's object challenges the limits of current astrophysical knowledge, suggesting that the universe may harbor mechanisms and patterns that we have yet to identify. While some fringe theories have even entertained the notion of intelligent or artificial shaping, mainstream science treats such ideas cautiously. The prevailing perspective remains that natural processes, however rare and finely tuned, are the most likely explanation. Nonetheless, the debate between coincidence and design underscores the galaxy's profound impact on our thinking. It compels astronomers to explore scenarios beyond ordinary models, and to acknowledge the possibility that nature itself can produce structures of remarkable order and beauty. Ultimately, whether Hoag's object is the product of chance or an unknown guiding principle, it functions as a natural laboratory for exploring the boundaries between randomness and order in the cosmos. Its existence forces a reconsideration of the assumptions we make about how galaxies form and evolve, and invites reflection on the delicate interplay of forces that can produce such astonishing regularity. In this sense, the debate itself, between coincidence and design, becomes a valuable tool for understanding not just Hoag's object, but the broader principles that govern the architecture of the universe. One of the most striking aspects of Hoag's object is the eerie precision of its structure, which extends far beyond mere visual appeal to challenge our understanding of cosmic mechanics. The luminous yellow core sits almost perfectly at the center of a vibrant blue ring of young stars, with a remarkably uniform gap of darkness separating the two. Across hundreds of thousands of light years, this alignment is astonishingly precise. Deviations from circularity are minimal, and the ring maintains a consistent thickness and brightness around its entire circumference. In a universe dominated by gravitational chaos, where galaxies are continuously influenced by nearby neighbors, dark matter clumps, and internal turbulence, the odds of achieving such alignment through purely random processes are staggeringly low. This perfect geometry is what gives Hoag's object its almost otherworldly quality, as if some unseen hand arranged the components with deliberate intent. The improbability of such precision becomes even more apparent when considering the dynamic forces at play within and around the galaxy. Stars in the ring orbit the central core under the influence of gravity, while also interacting with each other through localized perturbations. Over millions of years, these interactions tend to distort stellar distributions, leading to clumps, arcs, or irregularities in the galactic structure. Yet Hoag's object shows remarkably uniform spacing and velocity among the stars in the ring, indicating a finely tuned gravitational equilibrium that defies typical galactic evolution. Such a balance is exceptionally rare. Even among the small population of ring galaxies, few display this level of concentric perfection and rotational coherence. The uniformity extends to the gap separating the core from the ring, a feature that enhances the sense of cosmic precision. This void is nearly devoid of stars, gas, or dust, creating a striking visual and physical separation between the old central nucleus and the young stellar ring. Achieving such a clean gap would require not only that the stars in the ring form at a specific radial distance from the core, but also that no other matter drift into this region over billions of years. In most galaxies, gravitational disturbances, star migration, and residual interstellar material would gradually fill or blur this space, making Hoag's object's clear and enduring alignment all the more remarkable. Even when compared with other ring galaxies, Hoag's object stands out for the consistency of its ring's orbital plane. Many ring galaxies display warped or slightly elliptical rings due to angular momentum misalignments, off-center collisions, or tidal forces from neighboring galaxies. In contrast, the ring of Hoag's object appears nearly perfectly circular when projected onto the sky, suggesting that the plane of the ring aligns closely with the central core's gravitational axis. This level of alignment across tens of thousands of light years implies a stabilization mechanism or a set of initial conditions that are extremely rare, further underscoring the improbability of the galaxy's geometry occurring through conventional processes. Some astronomers have proposed that the alignment may be the result of gravitational resonance or self-organizing dynamics within the galaxy. In this scenario, the core and surrounding mass distribution could guide stars into stable orbits that naturally produce a ring, while simultaneously maintaining a cleared-out gap. However, while mathematically plausible, such resonance requires a delicate balance of mass, velocity, and angular momentum that has yet to be observed elsewhere on this scale. It remains uncertain how such perfect symmetry could emerge and persist without external disturbances or internal irregularities disrupting the system. The alignment mystery is further amplified by the galaxy's isolation. Hoag's object does not appear to have close massive neighbors that could have nudged it into shape, nor does it show evidence of recent collisions that might have created the ring through a radial wave of star formation. Without external forces to guide its formation, the precise arrangement of the core, gap, and ring seems almost self-directed, suggesting that the initial conditions during its birth were extraordinarily finely tuned. This combination of isolation and perfect geometry makes the galaxy an exceptional natural laboratory for studying the limits of galactic self-organization. Ultimately, the alignment of Hoag's object challenges both probability and theory. Across cosmic distances, it is exceedingly rare to see a structure where stellar populations, voids, and cores are also perfectly concentric and balanced. Each feature, the luminous core, the clear gap, the evenly spaced ring of young stars, contributes to a geometry that seems statistically improbable, raising profound questions about how the galaxy formed and has maintained stability over billions of years. This precision is not merely an aesthetic curiosity. It speaks directly to the physics governing star formation, gravitational equilibrium, and the interplay between order and chaos in the cosmos. Hoag's object is a galaxy that, in its perfect alignment, forces us to confront the remarkable capability of nature to produce patterns that defy our expectations and challenge our understanding of the universe. Hoag's object poses a significant challenge to current astrophysical models, forcing astronomers to reconsider long-held assumptions about galactic formation and stability. Traditional frameworks for understanding galaxy evolution rely heavily on scenarios such as hierarchical clustering, mergers, and gradual accumulation of gas and stars. In most galaxies, irregularities, asymmetries, and chaotic distributions of matter are expected outcomes of these processes, driven by gravitational interactions, turbulence, and external perturbations. Hoag's object, with its flawless ring, empty intervening gap, and isolated core, directly contradicts these expectations, suggesting that there are mechanisms at work that our current models do not adequately account for. Its existence highlights the limitations of standard theories and emphasizes the need to expand our understanding of how galaxies can self-organize into extraordinarily stable, highly symmetrical structures. One of the primary challenges is the persistence of the galaxy's structure over immense timescales. Most models predict that rings created through collisions or resonance effects are transient, gradually dissolving as stars migrate, gas clouds dissipate, or interactions with other galaxies perturb the system. Yet Hoag's object appears stable, maintaining its nearly perfect circularity and central void for hundreds of millions of years. Such longevity implies either a rare set of initial conditions or the presence of stabilizing forces that conventional models have yet to incorporate fully. The galaxy forces astronomers to confront the possibility that some galaxies can achieve and sustain remarkable symmetry without the need for external sculpting or repeated interactions. The challenges extend to star formation as well. The hot, young stars populating the ring are evidence of ongoing stellar activity, yet the ring's formation and maintenance suggest a degree of regulation that current models struggle to replicate. In most galactic environments, star formation occurs in clumps and filaments, driven by localized gas density and turbulence. Hoag's object, however, exhibits a remarkably uniform distribution of newly formed stars along a circular ring. To achieve this, the galaxy must regulate gas density, angular momentum, and gravitational interactions across tens of thousands of light years, a level of coordination that challenges conventional star formation theories. Astrophysicists must now consider whether additional forces or feedback mechanisms, perhaps involving dark matter halos, magnetic fields, or subtle gravitational resonances, are contributing to this exceptional balance. The galaxy's isolation further complicates the picture. Most peculiar or highly ordered structures in known galaxies can be traced back to external influences, such as tidal interactions, collisions, or mergers. Hoag's object shows no clear evidence of a recent collision or nearby massive galaxies that could have sculpted its form. This absence of external drivers implies that the galaxy's unique morphology arises from internal dynamics or initial formation conditions alone. As a result, astronomers are pressed to explore models where internal self-organization can produce stability, symmetry, and a maintained gap between core and ring over cosmic timescales, scenarios that are not commonly represented in existing galactic evolution simulations. Another complication comes from the scale at which these phenomena occur. Hoag's object spans roughly 100,000 light-years, comparable to the Milky Way, yet every component, the central core, the intervening void, and the outer ring, is orchestrated with extraordinary precision. Most current models account for large-scale dynamics in terms of average properties or statistical distributions, yet Hoag's object requires explanations that reconcile order and stability across vast distances with local star formation processes. This multi-scale challenge forces astrophysicists to refine simulations and theoretical frameworks, ensuring that they can accommodate the possibility of rare but highly ordered galactic structures alongside the more common chaotic systems. The challenges presented by Hoag's object also extend to the question of galactic evolution pathways. If a galaxy can naturally maintain a near-perfect ring for hundreds of millions of years, it suggests that our understanding of the evolutionary end states of galaxies may be incomplete. Instead of evolving towards spirals, ellipticals, or irregular systems exclusively, some galaxies might follow atypical evolutionary tracks governed by a combination of resonance, angular momentum distribution, and internal feedback that stabilizes unique morphologies. This revelation expands the landscape of potential galactic forms and forces astrophysicists to consider whether Hoag's object is a rare anomaly or representative of a broader class of underobserved structures. Hoag's object has also encouraged re-evaluation of the role of dark matter in shaping galaxies. Dark matter halos are believed to influence rotational curves, star formation, and overall stability, yet the precise mechanisms by which a halo might facilitate the creation of such a perfect ring are not well understood. Observing a galaxy that exhibits stability, symmetry, and ongoing star formation while maintaining a central void suggests that interactions between visible matter and dark matter could be more subtle and sophisticated than current models predict. This pushes astronomers to explore new simulations and refine the parameters governing halo-matter interactions to account for extreme yet stable galactic configurations. Ultimately, Hoag's object challenges astronomers to rethink nearly every aspect of galactic theory: formation, evolution, stability, star formation, and the influence of internal and external forces. Its existence reveals the gaps in our understanding and underscores the need for more sophisticated models that can explain not only chaotic or irregular systems, but also highly ordered, long-lived structures that defy traditional expectations. By forcing the scientific community to confront these challenges, Hoag's object serves as both a puzzle and a guidepost, illuminating the complexities and possibilities of the universe in ways that few other galaxies can. It is a cosmic anomaly that demands both humility and curiosity, demonstrating that the universe is capable of producing order on scales, and with precision that current theories cannot fully explain. Hoag's object's extraordinary symmetry, combined with the vast emptiness separating its core from the surrounding ring of young stars, has fueled not only conventional scientific inquiry, but also more speculative, fringe theories. Some enthusiasts and thinkers have suggested that such perfection might hint at the possibility of advanced cosmic engineering. While these ideas are far outside mainstream astrophysics, they arise from a simple observation. Natural processes observed elsewhere in the universe rarely produce structures this precise, especially on a galactic scale spanning tens of thousands of light years. The combination of a pristine ring, a perfectly centered core, and a massive empty gap is so orderly that it inspires speculation about whether it could be the result of some intelligent or deliberate process. An artifact of a civilization operating on scales and technologies far beyond human comprehension. The basis for these theories often stems from the notion of megastructures or astroengineering, concepts popularized in both scientific and science fiction circles. Just as humans might imagine engineering projects on planetary or solar scales, theorists speculate that a civilization with control over stellar or galactic processes could, in principle, manipulate matter to create patterns of astonishing symmetry. Hoag's object, with its nearly flawless circular ring and clear separation of stellar populations, fits the visual profile of what a naturally occurring engineered galaxy might look like. While there is no direct evidence supporting the idea of artificial manipulation, the very fact that the galaxy's form appears so improbable naturally makes such speculation tantalizing. Some proponents of this fringe viewpoint point to the uniformity of star formation in the ring as a potential clue. In natural galaxies, star formation tends to occur in clumps and clusters, influenced by the stochastic distribution of gas and turbulence within the galactic disk. The even distribution of hot, young stars along Hoag's object's ring seems almost as if some guiding principle or mechanism has orchestrated their placement. From the perspective of cosmic engineering theory, such uniformity could represent a controlled process. Perhaps the deliberate formation of stars along a predetermined orbit, creating a structure that maximizes visual symmetry or optimizes energy distribution on a galactic scale. While this remains speculative, the regularity of the ring undeniably invites questions about the boundaries between natural and potentially artificial cosmic phenomena. The massive gap between the core and the ring further feeds these ideas. In most galaxies, matter is distributed more continuously, with stars, gas, and dust forming gradients from the core outward. The emptiness of Hoag's object's intervening space is unusual even among ring galaxies and appears almost intentional. Fringe theorists have suggested that if a civilization were capable of manipulating matter at galactic scales, clearing out this gap could be a method to maintain gravitational stability for the ring or to create a visually distinct and aesthetically coherent structure. Again, this remains entirely speculative, but the very improbability of such a configuration occurring naturally lends itself to imaginative hypotheses about intentional design. It is important to stress that mainstream science does not endorse the idea that Hoag's object is artificial. Astrophysicists focus on natural explanations, such as resonance, unusual collapse conditions, or rare forms of galactic evolution. The artificiality hypothesis remains a speculative fringe idea, largely because there is no empirical evidence for intelligent intervention and because known physical processes, while incredibly unlikely, could theoretically account for the galaxy's structure. Nevertheless, the very fact that some researchers and enthusiasts even consider such a possibility highlights the profound impact of Hoag's object on the human imagination. It is a structure so orderly and beautiful that it challenges not only our scientific understanding, but also our sense of what is possible in the natural universe. What is particularly compelling about these discussions is the broader philosophical question they raise. Hoag's object forces observers to confront the limits of natural probability and the possibility of phenomena that appear designed without necessarily being the product of intelligent intervention. Whether one interprets it as a cosmic coincidence, a result of rare astrophysical conditions, or the tantalizing hint of advanced cosmic engineering, the galaxy's perfection pushes the boundaries of human imagination and scientific inquiry alike. It serves as a reminder that the universe is capable of producing forms that challenge conventional understanding, blur the line between natural and artificial, and inspire speculation about the far reaches of possibility in both physics and philosophy. Ultimately, while the notion that Hoag's object could be artificial remains speculative and outside mainstream science, its extreme symmetry and improbable geometry make it an enduring subject for contemplation. Even if it is entirely natural, the galaxy provokes questions about the extraordinary capabilities of the universe to generate order from chaos, leading scientists and enthusiasts alike to marvel at a cosmic structure that, in its perfection, almost seems to defy natural explanation. In this sense, Hoag's object becomes more than just an astronomical object. It becomes a symbol of mystery, prompting us to imagine the extremes of possibility in a universe that is still largely unexplored. Despite decades of observation and study, Hoag's object continues to harbour a multitude of unanswered questions that perplex astronomers and challenge our understanding of galactic formation. One of the primary mysteries revolves around its exact origin. While several theories have been proposed, including collisional scenarios, gravitational resonance, and rare collapse of a proto-galactic cloud, none can fully account for the galaxy's perfect symmetry, isolated central core, and empty gap. Unlike other ring galaxies, whose formation can often be linked to interactions with neighboring galaxies or dramatic collisions, Hoag's object appears relatively isolated, leaving scientists without clear evidence to confirm which mechanism, or combination of mechanisms, produced this extraordinary structure. Its origin remains, in many ways, as enigmatic as its appearance. Another unresolved question concerns the galaxy's long-term stability. Hoag's object has maintained its striking ring structure over millions of years, but the processes that allow it to remain coherent while supporting ongoing star formation in the ring are not fully understood. Galactic dynamics are typically influenced by internal interactions, gravitational perturbations, and the distribution of dark matter. Yet the galaxy's ring shows remarkably uniform thickness, orbital regularity, and even spacing of stars. Understanding how such stability is maintained over cosmic timescales is a significant challenge, as most natural models would predict gradual diffusion or distortion of the ring. Whether the galaxy's current configuration is temporary, or whether it has been stable for billions of years, remains an open question. The role of the central core is also a subject of ongoing investigation. Astronomers suspect that the yellow nucleus may be an older elliptical galaxy, but its precise composition, age distribution, and formation history are not definitively known. How the core interacts gravitationally with the surrounding ring, and whether it played a central role in shaping the ring's formation, is still unclear. Furthermore, the stark contrast between the old, yellow core and the young, blue stars in the ring raises questions about how star formation was ignited in such a uniform pattern at a consistent distance from the center, and why the space in between remains largely empty. These aspects continue to defy explanation through conventional galactic evolution models. The question of whether Hoag's object is a one-of-a-kind galaxy or part of a rare but undiscovered population remains unresolved as well. True ring galaxies are extremely rare, and those that approach Hoag's level of symmetry are even rarer. While astronomers have identified a few other ring galaxies with similar features, none are known to perfectly match the scale, alignment, and uniformity of Hoag's object. This raises important questions about whether the galaxy is an extreme outlier, a survivor of an uncommon evolutionary pathway, or simply one of a larger group of unusual galaxies that have yet to be observed. Given the vastness of the universe and the limits of current observational technology, It is entirely possible that other galaxies with similar morphologies exist but remain undetected. Further complicating matters is the interplay of dark matter within Hoag's object. The influence of dark matter on the galaxy's formation, ring stability, and star formation patterns is not fully understood. While dark matter is thought to provide the gravitational scaffolding that allows galaxies to maintain their shapes, the specific distribution and density required to produce such a pristine ring configuration is unknown. Could a particular halo of dark matter have guided the formation of the ring while preserving the gap? Or is the distribution of dark matter in Hoag's object entirely conventional, making the galaxy's perfection even more improbable? These questions remain open and fuel ongoing research and simulation efforts. The galaxy's ongoing star formation adds another layer of mystery. How the hot blue stars in the ring continue to form at a steady rate while maintaining uniformity around the circumference is not fully understood. Most galaxies experience uneven or stochastic star formation, influenced by turbulence, gas clumping, and feedback from previous generations of stars. Hoag's object, however, exhibits an almost regimented pattern of stellar creation, implying that some stabilizing mechanism, whether gravitational, magnetic, or otherwise, might be at work, though its nature is currently unknown. Finally, the fundamental question of cosmic significance looms. Does Hoag's object represent an extreme but natural outcome of galactic evolution? Or does it hint at processes we have yet to comprehend? Its isolation, symmetry, and internal coherence challenge nearly every assumption about how galaxies behave, forcing astronomers to confront gaps in existing theory. Every observation raises further questions about the interplay of forces, the role of initial conditions, and the potential existence of other galaxies with similarly extraordinary features. In essence, Hoag's object is a cosmic puzzle whose pieces remain only partially understood, leaving scientists with as many questions as answers and reinforcing the profound mysteries that the universe still holds. Hoag's object, with its perfectly circular ring, pristine central core, and vast intervening gap, stands as one of the most awe-inspiring reminders that the universe is far stranger and more complex than we often imagine. It challenges our assumptions, defies conventional models of galactic formation, and raises questions that remain unanswered even decades after its discovery. Its existence compels us to confront the limits of our knowledge, reminding scientists and enthusiasts alike that the cosmos is capable of creating structures that seem almost impossibly ordered, as if nature itself is experimenting with forms beyond our comprehension. The galaxy's mesmerizing geometry invites not only scientific inquiry, but also philosophical reflection. The symmetry and balance of Hoag's object evoke a sense of harmony and precision rarely seen on cosmic scales, prompting us to reconsider what is possible in the natural universe. It encourages the contemplation of mechanisms that may guide galactic evolution in ways we do not yet fully understand, from gravitational resonance and dark matter dynamics to potential feedback processes that stabilize star formation across vast distances. Every observation, from the uniformity of the ring's stars to the emptiness of the gap, reinforces the notion that the universe can surprise us with structures that challenge both expectation and imagination. Beyond its scientific significance, Hoag's object embodies the human fascination with cosmic mystery. It captures the imagination precisely because it appears so improbable, almost as if the universe itself has presented a puzzle that defies the rules we thought we understood. Its isolation, stability, and perfection transform it from a mere galactic object into a symbol of cosmic possibility, a reminder that even in a universe governed by physics and gravity, chance, rarity, and perhaps unknown processes can converge to create astonishing beauty. Ultimately, Hoag's object is more than a galaxy. It is a window into the unknown, a celestial enigma that inspires wonder, curiosity, and humility. It reminds us that despite centuries of astronomical discovery, the universe still holds secrets capable of challenging our deepest assumptions. As we gaze upon this extraordinary ring of stars encircling a lonely core, we are reminded that the cosmos is far more intricate, mysterious, and breathtaking than we can ever fully comprehend, and that each discovery, no matter how improbable, expands the boundaries of human understanding and awe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.